to introduce our speaker today?
Sure. So we all kind of had a lot of excitement about the Klein paper recently, and we have talked about it. That's from Shizhe. He's also kind of at NVIDIA, and did his PhD previously at Hong Kong University of Science and Technology. And he's going to tell us a little more about his journey. He climbed his way through this.
Thank you. Yeah, hi, hello everyone. I'm Shizhe Diao, and I'm from data research working on data efficiency in both pre-training and post-training. So it's a great honor to be here today, and I'd like to thank Prayush for the kind invitation. Recently, I've been working on a project about the data curation, especially the data clustering and data filtering and data mixing for the pre-training language models. And I know many of you are already very experienced in data curation and probably much more than I am. So I also look forward to learning from your perspectives and having productive discussions with you. Yeah, so today I'll walk you through how we design a comprehensive data curation pipeline starting from unstructured web data, focusing on core components such as clustering, filtering, and mixing. Yeah, so modern language models are trained on massive unstructured web data, often containing trillions of tokens collected through large-scale web crawls. This unstructured nature makes it difficult to understand the data's composition and poses challenges for systematic data curation. So early research efforts focused on assembling data from well-known sources such as Wikipedia, GitHub, and books, resulting in datasets like the Diao. However, a key question quickly emerged. So how should we mix and balance data from different domains? So this gave rise to research on data mixing strategies. And as pre-training demands grew, researchers realized that these known sources were insufficient to scale further. They turned to crawling the web, open web, so leading to datasets like the ComCrawl, Zuda, and the DCRI. So more recently, NVIDIA released the Neutron CC, which is a filtered version of web crawl, and this shift raised a new challenge, which is how to organize and mix data to construct a good data blend when data domains, the domain labels are missing. So because web data is unlabeled and highly scattered, so it is essential to first organize the data, for example, by clustering similar content before applying data mixing strategies to construct effective data blend. And okay, here are some of our expectations. Firstly, of course, we need high quality data, which could achieve better data efficiency. Ideally, if we could reduce the amount of data while achieving the same effectiveness, that would be perfect. And additionally, there are many previous data filtering approaches, but most of them are focused on the model-based filtering or heuristic rules. And also, we believe that both diversity and quality of data are equally important, but obtaining sufficiently diverse data is challenging. So at the same time, the quality of the same piece of data might be considered high in the financial domain, but might not be relevant in the medical domain. Thus, we aim to optimize the both specific domains. Finally, even if we have sufficiently diverse data, figuring out how to mix them effectively is also a challenge. To address these challenges, we have formulated data mixing as an optimization problem and trained a predictor model to predict the data mixture rates. Okay, so before introducing our approach, I would like to introduce some of our preliminary results in our pilot study. We explored several specific ideas that we believe are particularly important. The first one is an unsupervised approach clustering. We feel that clustering has been overlooked and underestimated in prior work, especially in large language model training. However, it is a powerful method for discovering domain-specific data. So this approach can effectively leverage large-scale semantic information, which is crucial for evaluating both the quality and diversity of clusters. In contrast, most previous pre-training data curation methods have focused on heuristic rules or model-based filtering. In addition, we extend the traditional concept of a quality classifier to a more fine-grained approach. Specifically, we prompt teacher models to generate data and use their feedback to train classifiers. And these classifiers are guided by well-defined criteria and highly efficient. So these two ideas, clustering and classifier training via teacher feedback, are orthogonal yet complementary. So they construct the idea of column clustering. And the goal of column clustering is actually to reorganize the web data and to transform unstructured, unsupervised web data into well-organized domain-specific datasets. And the next challenge is how to effectively mix data from different clusters. To address this, they also explore lightweight proxy models and the training of predictor models for data mixing. Okay, let's look at some details. First one is clustering. There are several steps. We firstly convert text to embedding vectors using a good off-the-shelf embedding model, and then we use the embeddings to do k-means clustering. Of course, we could try other clustering algorithms, but we found that k-means is good enough. It is very efficient and effective. And next is pruning. After getting too many clusters, we need to identify the cluster quality and remove those low quality clusters. And here we are using Euclidean distance to measure the similarity, and we found that it is a good metric to capture the domain's characteristics. For example, the data can be clustered with different. For example, the data could be clustered with different topics, and for example, like interviews, corruptions, and so on. This indicates that if we would like a specific distribution, we can easily retrieve from the cluster information. For example, if we are concerned with the mathematical task, we can find relevant clusters from mathematical domain.
Or if you want eternal darkness and corruption, you can sample from the eternal darkness and corruption cluster. If you want to try a demon.
So like, how do you get these topics?
Oh, basically, the topics are labeled by some off-the-shelf models, for example, GPT-4.
You give it like a few samples from each cluster? Or like
Yes, for example, 100 samples. Yeah, and ask the GPT-4 to annotate the topics.
And this is just for us to see, right? These labels aren't actually used. Okay.
Exactly.
What is the quality again? Maybe I missed it. How do you define quality in the cluster?
Oh, yeah, I will define it later.
Okay.
Later slide.
Yeah.
Maybe a related question. What was the process for like choosing an embedding model? There's like many, how do we decide?
The embeddings, right?
Yeah.
Yeah, the embedding models, as you can see, they showed leaderboard for the embedding models. Right?
Okay.
Yeah,
we
there's a
took a
leaderboard.
okay.
Yeah.
Okay.
We would like to choose the best embedding model, of course, but we need to balance the efficiency.
I see.
Yeah, because we found that the top 8, almost the top 10 models are around 7 billion parameters. Yeah, and we find that 7 billion parameters is very costly for us. And instead, we choose, as you can see, the number 6, the Stella model, which is a 400 million model. Yeah, it's great.
I see.
And did you just pick one, or did you try different one?
Oh, we only take one currently.
Yeah, just one. Okay.
Yeah, but it's a good idea to try different models and meet some of them. Yeah.
Also for k-means, like how do you select things like how many Android, or is that something automatic, or do you do it in like multiple levels?
Do you mean the number of clusters, the number
Yeah.
of centralized? Right?
Yeah.
It is based on heuristics and experience, and also we did some ability studies, and I will show you later. Okay.
I'm curious to know, like, if you have a document that, sorry for asking like, many questions here. So if a document is OID to the embedding model, how would actually GPT actually enable that cluster?
I mean, if we have a new document out of the distribution.
Yeah, for the embedding model, because you embed, you cluster, and then you give some samples to I don't know, like to GPT instead of something like to enable the cluster, right?
Yeah, basically there are two steps here. Right? First is the embedding and clustering with the embedding model. Because the embedding model is trained on the web data, so basically it has seen a large distribution. It has already seen such a large distribution, and basically it is also based on the semantic meaning. For example, the combination of different words, and it could deal with the new document.
Yeah, something could be like kind of OID, could be like, I don't know, legal domain code, it's like very hard and the embedding might collapse, like for the examples that the model was not trained on. So we might have a cluster of examples that are unknown for the model.
Yeah.
Right. And then when we label them, what would we expect the label to be?
Yeah, actually, it poses challenges if the document is not a distribution to the embedding model. But for the labeling, for the annotation with GB4, it doesn't matter because it does not play a role in our method. It's just for visualization. Yeah. Yeah, thank you so much for your question. Okay, so with the data clustering, we did some qualitative analysis with several findings. Firstly, clustering could do deduplication. We know we can use minhash to do deduplication, right? While clustering could provide us another tool with considering more semantic information. This finding is not surprising, and it is also consistent with the previous study, which is called semantic deduplication. And more importantly, clustering could indeed help us identify bad data, especially semantically. For example, we provide some garbage prompt as prop and try to assign them to different clusters. For example, here, this is document. We manually design a document with lots of grammatical errors. And for example, advertisement, repeated sentences, excessive special characters, and garbage content. And very interestingly, we found that the advertisement document will be assigned to the cluster number 163. And if we manually check this cluster, we will find that basically all of this cluster contains a lot of advertisement documents. Yeah. So basically, it indicates that clustering will help us group the bad data together so that it makes it easier to identify bad data, and we can easily remove them with some props. Yeah, and also that's the basic idea of clustering. And in terms of the quality, the second idea is the neural classifier, which is to evaluate the quality of clusters. So the core idea is to leverage larger teacher models to distinguish high quality data. As we know, teacher models could help us improve the student model in many different ways. One could use it to do distillation. Of course, we can use it to generate synthetic data. But here we would like to restrict the usage of teacher models to do verification. We argue that verification is easier than generation, given that we don't know the knowledge boundary of teacher models, and we would like to minimize the risks of hallucination. So we only use larger models to provide verification instead of generation. So ideally, we could ask a larger model to go through all of the pre-training corpus, but considering the raw corpus would be huge, it's like 15 trillion tokens, so it would be very costly if we rely on the teacher model. And so we expect we could transfer the discriminative ability from the teacher model to several smaller models, but they should be efficient. And then we design the following steps. Firstly, we will prompt large teacher models to evaluate a small amount of pre-training data, and then we will use the teacher model's judgment to train several model-based quality classifiers. Here we are using fast text, which is very efficient. The final step involves reviewing all of the clusters, sampling a subset of examples from each, and using the classifier to assess the quality of those samples. So based on the average assessment, we will determine whether to return the cluster or not. And here we show the prompt template we used for the teacher models during annotation. We designed 4 criteria, including quality, advertisement, informational value, and education value.
So does the 4 scores gets averaged, and how do you pick the threshold on what to put there?
Yeah, actually, it is like a philosophy of engineering, like data engineering. So we will evaluate separately, evaluate based on these 4 scores. We will get 4 scores based on these 4 perspectives, right? And then we will do some combination. Like we will manually set the threshold for each criteria.
I see.
Yeah.
So do you think like this 4-stage more granular labeling, fine-grained labeling helps you get more information? Because I remember there was an Ask LLM paper, and there was also a little bit better, but not that much. Do you think like this, like now you have 4 access to like more toggles to tweak, you can extract more this way? Because that's interesting, because when I read Ask LLM, I felt like results are not like helping that much as the cost of using a big model was. But maybe like now with 4 different axes, you can, as you said, you can set different thresholds. Do you think it gives you more leverage by having?
Yeah, actually, it's pretty tricky to balance like the number of criteria, and because if we get more criteria, of course we could get more fine-grained like evaluation, right?
Yeah.
But it would be become pretty hard to assemble them, to do assembling. How can they choose? How can they combine the different criteria?
Right.
If you cluster all the sample based on these 4 scores, do we see like different clusters of different axes where maybe we see like high information value in some samples but low education value?
Yes, of course. Yeah, maybe we find that.
Also, I noticed the prompt here is in the information value here is like +1 for at least accurate factor relevant information, right? How do we mitigate if the model is actually hallucinating? Getting that like this is actually accurate or not?
Yeah, that's a great point. So basically, I would say, in our paper, although we have 4 criteria here, right? In our paper, we do not use information value because we find that it is not very accurate. Okay, it's not helpful. Yeah,
that's good.
Yeah, and we find that the number 2 and number 4, the advertisement and educational value will provide a more clear boundary. Yeah.
Could you have like clusters that are like very, you probably you want to remove like clusters that are advertisements, right?
Yeah.
But could there be clusters that are advertisements of high informational value?
Yeah, of course. Yeah, that might be a case. Yeah.
But do you keep those?
Yeah, it depends on our like application scenario. Yeah, for example, if we actually we found that there are a lot of such examples. For example, it is an advertisement, but it is of high information value. For example, it even contains some mathematical calculations. Yeah, inside that example. Yeah, but in our paper,
I'm not getting those ads.
It's in the scope for the APR is gonna be like 60.
I have a question here. This prompt seems like I don't know, it contains I think like 20 points.
Yeah.
So how can you make sure that actually this prompt is not too hard to the model? Like what model did you use here? Like for example, if I have a small model, how can I make sure that
currently we are using a large model, the Neighbortron 340 billion model.
So okay, for example, if I have a 7B or a 70B model, like do you think it's better to give it like a long prompt like this, or maybe divide it into 4 prompts and then taking like a score by like 4 times?
Yeah.
How can I validate that actually?
Oh, actually, we could like keep a small subset as a validation set. We can evaluate the accuracy or precision of the report on that set after such annotation.
Actually, one other question is like, do you think like the scores here match the clusters you made in the past, or like they're very like are they like different, or like do all the things with 5 on that doesn't actually end up in the originally same cluster that you made in the past with your semantic clustering and that?
Oh, actually, I think these 2 approaches are complementary. We will first do the clustering, and then based on the cluster, we will do the filtering based on these 4 criteria.
I see.
Yeah, we did not do clustering based on these 4 criteria. We just do filtering.
Yeah, I was wondering if the clustering and the filtering like give the same thing. Like if like all the clusters with advertisements were actually all the scores with score 5, like also like considered.
Oh, actually, check that. We conclude that the cluster is actually very like compact. For example, if that cluster is annotated as a advertisement, actually,
It's very compact.
yes, actually like 99% of the contents are advertised. Yeah, I can basically let's see this example. Yeah, as you can see here, we pick the new class with high quality buckets. This is our starter data, and we cluster it into 1K clusters. And then we train several classifiers like advertisement, educational value, and then we apply such classifiers to filter bad clusters to identify them first. As you can see, here, this is basically a JSON file, and we can see that most of them are garbage contents. And you can imagine similarly for the similar phenomenon happened to advertisement. And of course, we found that it also help us to identify the adult content. Yeah, which would be very helpful to remove the toxic data. Actually.
Did you at all think about working like individual sample level filtering versus cluster level filtering?
Oh, actually, if we are working on the instance level, it will be more costly, right? Compared with the
Because you just sample some amount per cluster.
Yeah,
to
yeah.
filter.
Yeah, exactly.
But it's interesting because like when I read the paper, I was actually struck by this is the first paper I had seen that did cluster level filtering. All the other papers that did clustering and stuff still did like instance level filtering. I'm curious, like it was just motivated by was it just motivated for computational efficiency, or did you also feel like there was like a denoising effect by going by cluster? Or what was the also I'm curious, how did you assign the score per
Yeah,
cluster? Because I didn't see that in the
yeah.
paper. That was
Yeah,
my other
yeah.
question.
Yeah, honestly speaking, the efficiency is our motivation because our group focused on the efficiency, both the data efficiency and the model efficiency. Yeah, so all of our research are motivated by the efficiency, actually. Yeah.
Wait, weren't the classifiers applied on the samples, individual samples? And then you apply it on the samples for the cluster, and then you probably do some sort of averaging of the scores.
Yeah. Basically, as we can see, let's imagine we have 1K different clusters, right? And for each cluster, we sample 100 samples from that cluster, and then we evaluate the quality with the classifiers.
So say that like a cluster somehow has less than 100 samples, we take everything, and then we actually average it, right?
Yes, average.
And then the sampling here is just uniform. Because sometimes like I think about like cluster density where like if I actually want to pick points within the cluster, I want to pick points are actually far apart, so I can actually capture diversity within the cluster.
Yeah, that's a good point. Yeah, we just did the uniform sampling.
I see.
Yeah, that's very good.
Actually, even when you were saying you label the cluster, I was thinking like, should you put the centroid and like closer examples to get the right label, or should you go? Actually, I was discussing this with Amro and Friday. So, like, how should we like sample the examples to label the cluster?
Yeah.
But you do it, yeah, uniformly.
Yes, currently we do uniform sample.
Yeah, in the spirit of this, I'm curious, like the organize a web paper,
Yeah.
split things up into like topic and like style, right?
Yes.
And like K-means was mostly about like topic and not about style. So like that means that like a cluster would contain, in principle, you could imagine like a cluster containing different styles, and perhaps like your scoring method here is not uniform across styles. So yeah, I'm kind of like I'd be kind of curious, like when you were describing this, I was kind of hoping that like you want these scores to maybe kind of be like orthogonal to the cluster a little bit, right? So that you have like you want like to maximize the number of things. But yeah.
Yeah, so I'm concerned with like more dimensions in addition to the semantic meaning, like the format and styles, or is it?
Yeah, I guess like it may be a similar question to what Prajush was saying. Like, maybe the question is like we didn't have time, but like, or the answer is we didn't have time. But like, I'm concerned. I'm wondering if like 100 samples is enough, and like if you did see enough, like if a cluster is not homogeneous enough, then like did you want to like split it up into other stuff or?
Yeah. I see your question. So as you can see here, we tend to use a relatively large number of clusters. Yeah, so that we hope that we could group the data into fine-grained. Yeah, so that we hope the
So the fine grain is from the top, from the beginning.
Yes, exactly. The fine-grained promise. Yeah, okay. So I also have some quantitative results. Okay.
It happens every day. They take it. Right.
Yeah, so here are some quantitative results. The first row is the performance of the original name-consistent high quality bucket. The second row is after the clustering-based data filtering. We can see that such clustering does not hurt the performance, but reduces the data size. And also it offers gains to NMU and the mathematical tasks. Especially note that the original data here is of very high quality. This is the highest quality subset from name-consistent. So if we can apply such process to a larger, lower quality data set, for example, the whole control, we can expect even greater improvements.
So sorry, let me just make sure I understand this. So you took 500 billion Neutron CCHQ tokens, or you took Neutron CCHQ, which is about 1 trillion tokens, and then sample it down to 500 billion?
Oh, actually, the neutron CC, it contains like trillions of tokens, right? And it contains like 20 different buckets.
Yes.
Yeah, and here, this experiment, we started from the neutron CC high quality, which is the highest quality bucket. So naturally, it contains 500 billion.
Okay, oh, that's true for starting with 500 or trillion. Okay, and then you filter that down to a smaller data set
Yes.
of what size?
Oh, actually, like say here,
Ah, I see.
yeah, initially there are 1K cluster, and we figure like 105 clusters out.
Okay.
So this is removing about 10% of the data?
Yes, we
Of
will
the
do
clusters.
fantastic.
Not the
So
data,
the,
right?
the training is 10% faster then?
Yes, basically, yes.
Okay, and then, okay, so then you're training a what size model on this?
Here is like a 1 billion model.
Cool.
What is minus good?
What?
That's a filter.
Oh, it's a plus. Actually, it's will be plus.
It's plus.
Or filter out. So it means neutron is a high quality after the clustering-based data filtering.
Okay.
Yeah.
On the note of like reducing the model's toxicity, is it something that evaluated in some post-training evals or like just like manual inputs of the model, I guess?
Could you say it again?
Like so previously in the clustering and whatnot, you said you identified a lot of low quality data.
Yes.
And also a lot of toxic data in this case.
Yes.
So but here if it has great potential to reduce the model toxicity, is this something that you guys have validated through some other toxicity evals or just
Oh,
manual checks?
yeah. Currently, I do not have numbers of the toxicity benchmark. Yeah, but this is our ongoing work. Yeah.
Have you tried in some way to remove more than 125 clusters? Have you tried to remove more data?
Oh, this is our pilot study, and we can see in later slides they will show. Yeah, cool. So that's all about the our pilot study. So next, I will combine these useful findings and propose a new approach. Yeah, and before that, do you have any further questions regarding the pilot studies? Okay, cool. So let's dive into our CLAM framework. So there are basically 4 steps. Firstly, we embedded all documents into semantic space. Secondly, we group all documents into N clusters via clustering algorithm. And thirdly, we identify and filter bad clusters with our quality filters and merge good clusters into N super clusters. And with the remaining high-quality clusters, we propose a bootstrapping method that leverages a lightweight proxy model to iteratively search for the optimal data mixture. So it works like this. So we first initialize a distribution initialize the distribution and sample a set of different configurations. So let's say we get N1 different configurations, and for each configuration, it is a set of data mixture. For example, this 0.1 means we will, during the pre-training, there's 10% probability to select data from cluster 1. And so basically, you can imagine each configuration is actually a weight vector. And with all of these configurations, we could train our proxy models, which are smaller than our target model. So with the proxy language models training, we could get the performance with some metrics. The metric could be the validation loss on pre-training data or on downstream tasks data. So in our paper, we used the validation loss on 3 downstream tasks data and generalized to all 12 data tasks. And with the input as the configuration and the output as the target value, we can train a regression model to predict the target value given each configuration. So then we will get a predictor model here. And with the predictor, we could do another round of data mixture search. That is why we call it mixture bootstrapping. So in the second iteration, we will start from the best data mixture in the first iteration, and we could do pruning with our predictor. Because as you can see here, with the predictor, we do not need to run the proxy language model training. This pruning will greatly reduce the search space and accelerate the search process. Yeah, so that's the whole
So
idea.
when you say proxy models, like what? How big is it? Or like
Yes.
maybe you want to tell it in the next.
Yes. So for the proxy models, as you can see here, actually in our experiments, we have trained 4 sizes of transformers, like 62 million, 100 million, and 300 million, and 1 billion models. And in our paper, for the release details, we are using the 300 million transformer as the proxy model and the 1 billion transformer as our target model.
I have a random question about how, so if you go back a slide, when you're doing so when you randomly sample the cluster mixtures, right? So
Yes.
10%, whatever. How was that? Was that like, did you make them sparse? How did you, because I guess ideally you kind of want to make them sparse, right? Because later on you're going to prune them. How do you select the distribution of the mixtures?
Yes, that's a great question. So actually, we are using divisionally distribution to sample the data, to sample the considerations. Yeah, and actually, as you know, during the sample process, there are some parameters like strength, so we can control the sparsity of the configuration. Yes, it's basically like a parameter.
How does it, I mean, it seems like, you know, the sort of mixture approach you take is fairly similar to a number of things that are published. You know, it seems like there are a number of variants of like, okay, train a bunch of small models on, you basically sweep over like different mixture distributions and then train small models on them and then fit like some, you know, regression or prediction model to it. And then, you know, find the loss minimum on the model you have fit to all of your models and then use that as the mixture. Are there sort of I mean, one difference that you guys have is you do this iteratively, which is, you know, a big difference between distribution methods. Like, basically, is my understanding of this at the high level correct? Like, is it like, could you basically say it's sort of like iterated regmix, or are there certain things that say like regmix does that or doesn't do besides the iterative component, of course, that you found were key here?
Yeah. Actually, regmix is a very relevant study, and we are inspired by them. And there are like several different. First is iterative searching, right? And another one is we are starting from the unstructured data, like live data, right? They are scattered everywhere, and I believe regmix was conducted research on the tile data.
Yeah, they were using human assigned labels, but yeah, whether the labels are wherever they come from, like you still have some notion of category assignment.
And another thing is the efficiency, because I remember in regmix paper they need like 500 training, proxy models training. Yeah, and here we would like to boost the efficiency by our iterative bootstrapping. I will demonstrate later. We are using like 100. We only need 100 proxy model training. So which means that there is a 5x efficiency.
Okay, so that's so, and I mean, is that just simply a function of like sparser sampling of the distribution over sort of sources or clusters? Because I mean, I think like the choice of, you know, you could sort of choose an arbitrary number of like mixtures to train on. Like there's nothing special about, I guess you guys just chose 100 and it worked. Like you could also just as well do this method with like 1,000 different proxy models and mixtures, or like 50 different proxy models and mixtures, right? It's just the granularity of the sampling.
Oh, yeah. Actually, if you use regmix, if you constrain the budget to like 100 proxy models training, it will not work so well, because here the iterative searching is the key. Yeah, because if we can imagine if we search in a very large space, which is like the Redmix doing. So it will be extremely challenging to search for the optimal data mixture. And here we propose to like search in the whole space with a relatively smaller amount of budget, and then they find the optimal direction and we go with that direction.
Okay, thank you.
Yeah, thank you.
I have a question. It seems like the number of iterations we would need to make this successful is directly tied to the number of superclusters that we have. Like if we have more superclusters, we probably need a few more iterations than, like right now you have 21 superclusters and you say we need 100 iterations. So is there a way to, are there any experiments, application studies that you have which show with larger superclusters? So right now from 875 clusters, you merge them into 21 superclusters. What if you had 100 superclusters?
Yes. So one thing, yeah, we have some application studies here. As you can see here, we evaluate on the number of clusters. The first number, like 48 to 2K and 1K, is the initial number of clusters. And the second number is the number of superclusters. Yeah, as you can see here, we tend to constrain the number of superclusters to be small, for example, 20 to 30, around something like that. Because if, as you can imagine, for the predictor model chain, we need at least such data points to train a predictor. For example, if you have 30 clusters, we need at least 30 data points, 30 proxy models. Right? Yeah. And so it's like a efficiency trade-off.
Like how much compute, like I'm wondering like how impactful the filtration step is. Like if you just clustered and then immediately did the regression stuff, like does that, like how much more compute would you need to like reach the same performance?
Oh, so sorry, the compute in terms of what?
For the search step. So
Also, you are asking about the how many compute we need for the search step.
I guess what I'm asking is like, say that you didn't do the filtration step and just like stayed with this, you know, like all 1,000 clusters, and then did search over that instead of like filtering 128 first and then like doing search over the remaining. Like,
Oh, we did the filtering. Actually, we did the filtering. So starting with the 1K clusters, and we did filtering, and then we merged them into the 21 supercluster.
I think,
oh,
if I understand the question is like, why filter if you can just like let the remnants or like let the climb out of the learn to
Yeah.
discard that?
Oh, I see.
yeah.
I see. Yeah. So, basically, in terms of us, it's like a low-hanging fruit because we find during the pilot study we found that there are some outlier clusters which are those the bad clusters. We could very easily identify them and remove them. So back out. And so that's why we did filtering.
Maybe it's also related to Price's question, is like the number of superclusters that you have changes the number of iterations.
Yes, exactly. Yes, it relates to the efficiency. Okay, cool. So so let's say our experiments. So we apply the plan across multiple phases to evaluate its effectiveness. And recently, it has become common practice to divide pretraining into several stages. For example, from phase 1 to phase 4. And the goal is typically to build a strong, like for phase 1, the goal might be to build strong common sense reasoning capabilities. In later phases, like phases 3 and 4, reasoning and interaction tuning data are often added to improve the performance of downstream tasks. And the terminology here might be confusing and inconsistent. So for instance, phases 2 to 4 are sometimes referred to as continuous pre-training or mid-training. So to mitigate, to maintain the clarity, so we uniformly refer all stages as pre-training, and we simply denote them as phases 1, 2, 3, and 4. And next, I will report the results for each phase separately. So for the implementation, we are using the 400 million model embedding model, and we are using k-means into 1K clusters. And for the cluster merging, actually in our paper, we did a more aggressive filtering. We reduce the number of clusters from 1K to 240. Yeah, and then we merge them based on the distance.
It does the central distance, right?
Yes, exactly.
So can you talk a little bit about exactly how you like both how you do the merging and also like how you decided on that approach? Like how did you develop the cluster merging heuristics that you ended up using? Was it like ablation studies or?
Yeah, actually the motivation of merging is like to reduce the compute because during the search process, right, we need to constrain to make sure the number of clusters to be small so that we do not need so much like searching iterations. Yeah, and that's why we would like to constrain the number of clusters to like 10 to 30 around Azure.
Gotcha. So, but I'm just curious because one thing you could do, right, is you could cluster to 1,000, filter by cluster, and then recluster to 30. But instead, you did a merging process. Like, what was the intuition behind the?
Oh yeah, it's just more straightforward like to
Okay.
save cost.
Okay.
Yeah, as you can imagine, if we have a super huge amount of data, the clustering also takes a lot of time.
Okay.
When you merge them, like, is it more of a greedy approach where if the two clusters central distances are super close, they actually merge them? But what if you actually have clicks where like 3 clusters, all of them distances are actually equal distance, they're actually very similar? How would the merging logic change?
Yeah, because here, as you can see, the merging is kind of more aggressive. So that case is very rare.
I see.
Yeah, there's no such case. Because they are reducing from 200 to 20 clusters. Yeah, merging.
And then like for the iterative bootstrapping is like do we use 64 samples to train the like GBM tree models?
Yes.
In that case, so the ratio you always get the 3x if you want to do more ablations because like when I'm training the model, the dimensionality depends on the number of remaining clusters that merge, right? So say that I've actually have like I don't know 300 clusters and then that might merge into 25 to 30. That becomes the cardinality for tree models, right? Do we also does that mean we have to do times 3 to search them for like I don't know, it's like 120 samples or something to train the tree model?
Okay, say it again. So
when we actually train the regression model, right?
Yes.
The number of samples required seems to be 64 right now, the first level.
Yes.
And then but does that mean that like if we ended up merging more clusters, have more than 21, do we also want to sample more?
Yes, basically yes. Yeah, for example, if we have 60 clusters,
then we have to do like 180 samples.
Yeah, maybe. Yes. Yeah, then let's see some results. So our first experiments are conducted on phase 2 pretraining, since we would like to use phase 1 to provide us a strong foundation model. So we trained 3 series of transformers on 10 trillion tokens, and then we use warm-up stable decay learning schedule. And then we use the 300 million model as our proxy model and 1 billion model as the target model. And the starter data we are using is the Neutron CC plus small error corpus. And Clam first grouped them into 21 clusters containing around 800 billion tokens. And then identify the optimal data mixtures and we compare. And here in this table, we compare Clam with some existing data mixing methods like Doremi and the RegMix. And the results demonstrate that our Clam outperforms Obislam methods consistently. And although we search for the optimal data mixture with the 300 million proxy model, the results could generalize to the 1 billion target model perfectly. Yeah, so this illustrates good transferability of Clam method between different model sizes.
For the random, are you clustering the data and then just uniformly sampling across clusters, or is it random based?
Yeah, actually, all of the results here are started from the clusters. Yeah, we obtain clusters first, and then we do random sampling from different clusters.
So when you say the clusters, is this the final 240 clusters or is this starting from the 1000? So for random, did you sample from the 240 filtered clusters or was it the original 1000?
The final 20. Go for it.
Oh, final rating.
Yes. And also, next, we compared our results with some existing sorter models. Yeah, you can see here, we used the same data mixture previously identified to train on 400 billion tokens, and then compare the resulting model against sorter baselines. As shown here, Clam achieves better performance among all sub 500 million and sub 1.2 billion models. For example, Clam is better than Llama 3.2 model. Yeah, and I think Llama 3.2 1 billion model is trained on around 9 trillion tokens. And here, our model is also trained on 10 trillion tokens in the phase 1 pre-training, and then we use 400. Actually, it's 400 billion tokens in the second phase. And in addition to optimizing towards general reasoning tasks, one important application of Clam is developing a domain specialist model. They explore searching the optimal data mixture for specific domains. Using the MMU as an example, which has predefined 3 domains, like STEM, humanities, and social sciences, and divided tasks into these domains. So we conduct experiments on each domain separately. We set the optimization objective as the performance on its validation set. So here we introduce a new baseline Clam method N, which directly searches for the best parameters on randomly sampled configurations using the target model instead of the proxy model. And as shown in this figure, the Clam method N shows noticeably better accuracy than random across all 3 domains. And this established the robust baseline for comparison. And in contrast, our proposed Clam methods consistently improve performance across iterations. For instance, for both 300 million model and 1 billion model, the Clam iter 3 significantly outperforms both random and Clam method. Yeah, and in addition, we can see a clear improvement over each iteration. Yeah, for example, from iter 1 to iter 3.
Is there a reason to stop at 3? Couldn't we actually do more?
Yes, of course, we can do more. Yeah, the only reason is
This is compute.
Yes.
So when you do these proxy runs are equal in compute to the billion seen token seen as the actual run, or is it different? Is the length of the training for the proxy run same as the standard run, or is it like lesser?
Do we in the Clam framework, right?
Yeah, how many tokens do you see for the proxy run?
Yeah, actually, the proxy model training uses less tokens. For example, for proxy models, we are using 40 billion tokens. But for the target model, we are using 400 billion tokens or more. You can use 1 trillion tokens.
So this graph is for the proxy score, right? Or is it for the targets?
Target score.
This is for the target model score.
Yeah, target model.
But the iteration is done on the proxy model.
Yes.
Well, but you have the 350 ones there, right? Those are the proxy ones. Yeah, but
Yeah. For the 300 million models, the proxy model and the target model is the same.
I see. But the length will be different. The duration will be different.
Yes.
The proxy 50 would still be 40, and the target 50 would be 400.
Yes.
So in practice, you probably wouldn't train a full target model at each iteration. This is for the paper. Like if you were just trying to make a good model and you weren't trying to track how well, you wouldn't necessarily train a 1B model for this many steps at each round.
Exactly.
You would just
Yes.
you just wait till you get to the final weights and then train.
Exactly. Yeah, that is exactly what we want to express. Like, of course, you firstly the search would be we want to see the first message is the search would be very useful, and the second thing is of course you can use your target model to do searching, right? Like if your target is to train a 1 billion model, you can of course use the 1B model to do the search, but this is an efficiency issue, right? Yeah, that's why we propose the language proxy model.
How small can the proxy model be?
The what?
How small can the proxy model be? Have you tried to explain this?
You mean the like using
How small
more
in size? How small in size can the proxy model be? For example, have you tried to use like a very tiny proxy model?
Oh yeah, so you can see we try like here 60 million parameters. Yeah, we applied on the sizes of proxy model.
Okay, 60 million, right?
Like 60 million, 100 million.
But the main result is the 351, right?
Yes.
Yes, okay.
Yes, exactly.
Okay.
Yeah, and we want to say that 60 million with the 60 million proxy model, it also performs very well. It's just not as good as 300 million. Yeah, but it's also a trade-off between the performance and the efficiency. Yeah, and so here are the application studies we applied on the compute. If we increase the compute, we can obtain better performance, and also we can balance the search process, like the depth and breadth. Yeah, and we found that we need to balance both. And the proxy model sizes, it could be reduced, like we can use 60 million model as our proxy model. And also, basically, we find that our method is robust to the number of clusters, and it is somewhat robust to the initialization method. Yeah, and based on these findings, we propose we apply CLAMP and they introduce two new datasets. The CLAMP Live is 1.3, actually it's 1.2 trillion token covers with 20 clusters. And our starting point changed to we are using 4LM plus inconsistency and also the synthetic part of inconsistency. Yeah, and
I have a question here. What if you start from a low quality data? What if you start like from a bad data? I would like, for example, that affect clustering, embedding, and everything.
Yeah, that's a great point. So basically, if we start from here, the motivation behind this is we just want to deliver the highest quality data. So we tend to use the high quality data as our starting point. But of course, we could use the low quality data. I think that part we will greatly boost the efficiency, because you can imagine in the previous slides we just reduced like 10% data, right, after filtering. But with a lot of local data, we will do more aggressive filtering. Yeah, it will greatly boost the efficiency. Yeah, and yeah, here are two data sets. The first one is Clam Lab. It is like a 1 trillion, 1.2 trillion token corpus. And another one is Clam Mix. It's 400 billion token corpus based on the identified optimal data mixture, and we extract the subset from the Clam Lab. Yeah, and we did the phase 1 pre-training as well. So we pre-train a model from scratch, and you can see the performance is here. We are absolutely better than existing public database like Neutron City, Small and DCRM, and yeah.
Excuse me.
Yeah.
For Climb Lab, how much filtering did you do? What's the percentage of filtering for Climb Lab? What's the percentage? How much data did you filter out from the starting point?
Yeah, so you mean the percentage for the filter?
Yeah.
Yeah, it's very low, like 5% to 10%.
Okay, because I think the total sums up to be like exactly 1.3.
Oh yeah. So actually, I would say this kind of lab can just only like 1.15 change.
So one thing I noticed in the paper is that CPT experiments tended to focus on just one or two clusters very strongly, whereas the pre-training you had a much broader distribution. Do you have a sense of like where this approach of kind of like clustering broadly and training is it more well adapted to the pre-training style where you actually like do want a diversity? Because it seemed to me that like diversity didn't really matter for CPT. Like it had diversity in the first 10 trillion tokens. Just really wanted to tune it to these evals. Where basically just trying to find data that looks like the eval might be a more direct route. Is that also your feeling? Or like, how did you, like, now that you've done both these experiments as a researcher, like, how do you reflect on the difference between the CPT and pre-training for this?
Yeah, that's a very good point. So in our analysis, we find that in the phase 1 pre-training, we find that the data mixture weights are relatively uniform. It's more even, and for the continuous pre-training, we find that the weights are more sparse. Yeah, so which means only some of the clusters plays a key role. So I feel that it's more about the model's capacity. For example, if they are training a model from scratch, the model does not know anything, right? So it needs more diverse data, right? So in this stage, the diversity matters a lot. And in the content safety stage, the model has already learned a lot of stuff, right? And maybe in this stage, the diversity and the quality matters a lot. As you can see, and also the domain target matters a lot, right? If we are optimizing towards specific domains, yeah, we need such type of data towards similar data distributions. Yeah, also that's also another benefit of this method. You know, it could be adapted to different scenarios.
When you cluster the Climb Lab, like, is it that all synthetic data is at one place and all the other data is at the other place? Like, because you mix small LM and two Nemotrons subsets, like these 20 clusters, like, are they like quite skewed in terms of being in the synthetic, or like, is it more topical? Like, how are these clusters? Like, do they, like, as compared to your starting point?
So I'm referring to the synthetic data. So
Right.
what's
So your
concern?
starting point for Climb Lab was these 3 data sets, right?
Yes. Yes.
One was small LM, one was Nemotron
Yes,
HQ, and one was the synthetic version of Nemotron.
Yes.
And then you clustered into 20 representative clusters.
Yes.
So now, in these clusters, is there a bias towards the sources?
Oh no, actually, we will combine mix them at the first stage. I mean, initially we will mix these 3 sources together.
Right.
Yeah.
And you cluster them.
Yes.
So when you cluster it, do you feel like some clusters are just small LM and some clusters are just synthetic?
Oh, that's a great point. So we didn't manually check them, but I believe that the small LL might be like outlier because they contain some code data. And the code data would be like an independent cluster, but it will merge some code data from the new data. Right.
I guess we're also running out of time.
Oh yeah, that's. I think that's all about the method, and also I have some results about scaling up, but it does not matter a lot. Just scale it up to.
I want to see the 8 billion results.
Do I have time?
Quick, yeah. Let's quickly.
Okay.
I mean, if people have things they need to go do, they should go. But also,
Oh yeah, sure. Yeah, I can quickly go through the details. Yeah, so we talked about the phase 1 and phase 2 pre-training, right? Next I will show phase 3 and phase 4 pre-training, which is our like internal focus in our language model pre-training. So and also we are curious about if we increase the first model to 1 billion model and increase the target model from 1 billion to 8 billion transformers. Yeah, and here we optimize towards only 6 categories. We did not do clustering here because these data have already been prepared by the product team. Yeah. So as you can see, we have SMT data, raw data, math code, and other like common sense data and mathematical data. Yeah. And as you can see, Climb place improves a lot. Actually, as you can see, we compare our method with baseline. Here the baseline is based on heuristics, and they were used in our last generation of Neutron model. Yeah, and with Climb, we could improve. See the average. We could improve like 1 to 2 absolute points. Yeah. Yeah, and here the model is transformer, and we only consume about 100 billion in this phase 3 and phase 4.
and it's an 8 billion per model.
Yeah.
So what's the difference between phase 3 and phase 4 here?
Yeah, so it's just like the data sources are different.
Oh, I see.
Yeah, for example, based on phase 3, there are some new data coming, like more code data, more reasoning data. They added and call it phase 4. Yeah.
And then you take that and you move forward, right?
Yes.
Okay, makes sense.
And you do the same. Do you do filtering on it, or is it just the iterative weights? And
Yeah, we did not do clustering and filtering. We only do the iterative bootstrapping.
So if you're doing iterative bootstrapping on like, was it 6 like human defined categories, does that mean you just remove one of the categories after like the first round of iteration? Or are you just doing, so sorry, can you go back to the last slide? Yes. So like you have six categories there. Naively, if you were to just directly port the algorithm, as you described, you'd like find some set of weights, and then basically remove the category with like the lowest weight on it and then rerun the weighting algorithm. is that what you're doing here? Would you just like, if multilingual got the lowest weight, would you just throw out the multilingual data? Or are you not doing this sort of like eviction stuff?
Oh, no, they will not throw any queries away.
Okay, so you're just iteratively refining the weights.
Yes, optimizing the weights.
I see. Okay.
What was the baseline, if you can tell?
Sorry, what?
What was the baseline?
Oh, baseline here, right?
Yeah.
Yeah, the baseline is just a data mixture determined by our previous, like training experiment. We were using that data mixture in our last generation models.
Okay.
Can you
So
tell
it-
us what changes the most?
Oh, yeah, sure.
It's two six-dimensional vectors basically, right?
Yeah, let me show you the, actually,
You have like the baseline mixers and the new ones?
sorry, what?
Yeah.
Okay.
Yeah, here, they show the proportions, the distributions. This is a pie chart. The first two are baselines, the first two, baseline one and baseline two.
Oh, so you increase the synthetic data, right?
Yeah, the biggest part is,
Oh, wait.
here is, sorry, not this one actually. Sorry, I did not prepare for that part, but I can see that the biggest changes is the SFT data. Yeah, actually, as you can see, there are 6 categories, right?
Okay.
Yeah, we greatly increase the ratio of SFT data.
So you increase the SFT data.
Yes, high quality rating data.
And I have one more question, like, how big was each of these tests? Because the SFT data might already be small, right? So, which means increasing it might have higher effect because creating like a single billion might be increasing it by 2x or 3x, right?
Yeah.
So do you think that has an effect here?
Yeah.
And the quality of it also is high.
Out